starting now. We're going to be studying magnetism. Before or on your way out the door, you want to pick up one of these. It's got 21.1 and 21.2, so your homework tonight is 21.1, or over the weekend. It is not difficult. It'll take you 5 minutes. It's mostly concepts and drawing things. All righty. So, we're actually, I'm not sure I'm going to be able to record this because I need to use my computer, but we're going to talk a little bit about chemistry and the periodic table. I wonder, yeah, I'm not sure how this is going to work out for recording purposes, but we'll find out. Probably not going to record, but we'll see. That's all right. Yeah, I don't know if I can project and record at the same time. Organizing the periodic table. And what do the big numbers for all of the elements in the periodic table, what do they represent? Number of protons. That is correct. So hydrogen has 1 proton, and it's number 1 on the periodic table, correct? Helium has 2 protons, so it's number 2. Beryllium is 3. Is that right? 4 is lithium. Lithium, then beryllium. Beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. That's about all I got. All right. There's a song. Has anybody seen The Big Bang?
We don't want to know it. Do you want to play that game?
What's the game?
Where you say an element, and then the next person has to say an element that starts with the last letter of the one the first person said.
That's a hard game.
Boron.
Nitrogen.
Neon. It usually ends in N, so you run out.
Nubidium.
Magnesium.
Manganese. Yeah, that was manganese.
That
was an M.
Molybdenum.
Molybdenum. Ooh, good. Molybdenum. Is it manganese. Millennium. No! That's Hg. Does that count? Oh, okay. Mercury! Oh, nice one. We're back to M's and N's. All right. Let's look at the actual periodic table. Oh, this might work. This might actually work. I think it does. Because it's a double screen thingy. Okay, so here's our friend, the periodic table. Hydrogen's on the far left, nitrogen's on the far right. Although I'm not getting the full screen. Let's try this. Woo, it's working. Okay. Sort of working. Yeah, there we are. Okay. Helium. Everybody heard of the helium shortage, by the way?
Yeah.
Yeah, it's hard to get helium balloons. Yeah, does anybody know why there's a helium shortage? Well, there actually were huge stores of helium from World War II because they used to use helium in dirigibles. First hour got a little confused between dirigibles and didgeridoos. What's a dirigible? A balloon. There we go. Yeah. So they used to use helium. Yeah. Well, before helium, what element did they use to float? Hydrogen. That didn't go so well because hydrogen's not lead. Hydrogen's very explosive. What was the name of the really famous? The Hindenburg blew up. But helium used to be something that was provided. A lot of the helium in this country was provided by the U.S. government, and they've sort of deregulated it because we don't use many dirigibles anymore. They use helium in a lot of medical applications. And so that's more important than, I guess, birthday parties, which I don't know. I love helium. But yeah, helium's getting harder to find. Why is helium so much better than hydrogen, and what do all of these guys have in common?
They don't react.
They don't react. They're noble gases. What makes them unreactive?
They have a full valence shell.
Yes, full valence shell. All your chemistry's coming back. So horizontally, the periodic table is organized by number of protons. Vertically, what do these guys?
Families.
They are called families. Thank you, Wesley.
Same number of electrons in the outer shell.
Yes, well done. They also called what kind of electrons? Valence electrons, yes. They have similar properties, right? So these are called the noble gases typically because they're unreactive, they're noble, they're like too good for the other elements. What's this family named?
The halogens.
Nice.
Yeah, the halogen family, and they have 7 valence electrons, so to make them happy, what do they need? 1 more. They tend to react with what family?
Hydrogen.
One.
Yeah, hydrogen's family, family 1, what are they called? Let me see if I can scroll over. What are these guys called?
Alkali.
Alkalis and these? Alkali earths. And pink area is what kind of?
Transition metals.
Transition metals, and that gets complicated. Why?
Because they all have charges and stuff, and they're messed up.
They have different amounts of electrons.
Yeah, their electron configuration gets a little bit tricky. We're going to talk about that in a minute. Interestingly enough, this is another little interesting aside. What's the life form element? The element, yes, carbon, which I like to call the slut of the periodic table. I did. Yep. Why?
Because everyone gets
It reacts with anything. That's right. It has no standards. Yeah. Carbon and hydrogen, carbon and nitrogen, carbon and oxygen, carbon. I mean, it really, it has, think about it, 8, 7, 6, 5, 4. It's smack dab in the middle of that giving up, gaining electrons. They think that there may be other life forms based on silicon, like in other places in the universe, for the same reason. Because it'd be very reactive, so they'd be silicon-based life forms. What would they look like? How would they be different from us? Robots. Yes, computer chips. They'd be fake because they wouldn't be carbon-based?
Maybe made out of diamonds.
Oh, that's silicone, but yeah, no, not like fake
Yeah, a
boobs.
bunch of breast
Okay. Now I understand where that came from. You really do live with all women, don't you, Ian? Yep, that's always. Hello!
Hello. We have prom pictures for Ryan.
Oh, Ryan's not here.
Okay.
Okay, that's it? Just Ryan?
Sure.
You're taking Ryan's prom pictures? No, don't give them to Matt!
Sure.
Oh my gosh, what was I thinking? I will keep them. Let's see. Let's look, shall we? I'm just looking at them. I won't share with anybody else. Oh, that's nice. Okay.
It's on camera.
Yeah, that's true. There's evidence. It's lovely. No, stop that. We can't. I'm the only one that can do that. Putting them away. We'll look at them later. I'm just kidding. Just kidding, Ryan. I would never do that to you because Ryan's actually missing this, so he's going to watch this.
Well, that's the funny part.
Maybe later. Okay. So let's go to the transition metals. Let me see if I can scroll over a little bit here. Yeah. Transition metals, there's a special way that chemists designate how the electrons fill in here. And these are the d orbitals, right? What orbitals are these two guys? The s's, the shape of those orbitals, the way the electrons spin around. Spheres, yeah. The p's are these yellow ones. What shapes do those have?
Dumbbell.
Yeah, they're dumbbell shaped, yeah. And the d's? Clover leaves. There's one that's like dumbbells with a donut around it. They got all some really funky shapes. There's a way to represent.
Oh, the zip.
Uh-huh. Uh-huh. There's a way to represent these. What do those lines, those horizontal lines represent? What do they mean?
Well, that could be two, like down arrows.
Yeah, these are the orbitals. And how many electrons fit in a single orbital?
Those.
2, correct. So 2, 4, 6, 8, 10. If you counted, what would we get? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? So as we increase the number of electrons in the d orbitals, how do we represent that in this sort of schematic? Arrows, right. Did Lucky do the single arrow thing? Okay. I don't know why chemists do that.
Like one side of it.
Yeah, it's like a one-sided arrow, right? All right, so that's scandium. Is that right? Okay. So titanium has 2 electrons in its d orbitals. Where does the second electron go? Right here or right here. Okay, now this is where, since we can't see you on camera, you have to participate audibly. Is it?
No.
Correct, it's this one. Why is it not this one?
Matt said so.
Oh, all talking at once.
It can be
Because
half
Matt said so.
Poly-exclusionary
It's
principle.
one of those happy
Pauli exclusionary principle. Well done, that is high five deserving.
That's extra credit.
You have the longest arms in the world. There we go. That was pretty good. Okay. Yeah, Pauli exclusionary principle says what, Matt?
That you have to fill up all the orbitals before you can go back in.
Team them up, right? Pair them up. Yes. Why is that? What's the basic principle behind why they're more likely to fill these shells first?
Electrons don't like each other. They don't want to be close to each other.
Exactly. They don't want to hang out with each other. Right. Okay. So now we're up to 1, 2, 3, 4, 5. Hello. What element is that?
iron.
Iron. And so on 6, 7, 8, 9, and 10, they will do this. Right now, why do I have to draw them upside down?
Opposite spin.
They are opposite spins. And what you just took your AP Chem test, right? So you got all this. Why the opposite spin?
They don't like each other.
Physics.
Strangely enough, this has to do with the fact that nature wants things to be in the lowest energy state possible. What do we call that? What's the word for that? Entropy, correct. It's also sometimes referred to as times arrow. Let me give you an example. The butterscotch jar that we are all very fond of. I know sometimes you have a bad day and you just need that little package of sunshine to cheer you up, right? So let's say that our friend Maddie B walks in and is a little clumsy and pushes the jar of butterscotch off onto the floor. What will happen?
We'll all kill that.
Broken glass,
Oh, I was gonna say.
entropy, more disorder, that's right. Does it take energy for the butterscotch jar to sit on my desk? Is it holding some energy in a higher level? Yeah, what kind of energy? Yes, gravitational potential, what else? There is butterscotch energy. Talk to me about that, Ian. Takes energy to be happy. Lord, I know that one. Hello? Yeah. It's, by the way, here's how you know. Here's how you know. If you walked in after Maddie had this horrible disaster with the butterscotch jar, and you saw the following. You saw the butterscotch, the glass everywhere. Shards of butterscotch mixed with glass. And in order to return to the happy state that Ian's talking about, the glass and the butterscotch went and jumped back on the desk, you would know that something was up, correct?
She's a witch.
Yes, reason 52, why Miss Nick's a witch. You would know that time's arrow was running backwards, right? It would seem ridiculous to you. Jim, you can stay, but you can't be distracted. So, time's arrow says that everything in the universe is tending toward disorder. Right now, the universe is expanding. It's still in its, it's searching for its ground energy state. And iron breaks the laws.
Ooh, rebel.
It is a rebel element. Let me show you what iron does. So, iron is 1, 2, 3, 4, 5, 6. The universe says we want things to be at the lowest energy state possible. That's why the spins are opposite. A little tiny moving electron produces a little electromagnetic field. Just a teeny tiny one. Imperceptibly small electromagnetic field. But in electron land, that's enough to feel it, right, if you're another electron. So these guys are always going to spin in opposite directions to keep the energy at as low a state as possible, except for iron.
Don't do it.
I know.
Yeah, it should be going here.
Yeah, you should flip.
This upsets you? This?
Yeah.
You want it to be like this?
Yeah.
Oh.
All right. The point here is that because iron breaks the laws of nature, those two little electrons, they're spinning together. Everybody do it. Ready? Make them spin together. Make them spin together. Make them spin together. Spin. Let me see your electrons spinning. The back row is off. Yeah, try making them spinning opposite. That's not that hard. Now spin together. Same way. Alex? Yeah, thank you. All right. Oh, wait a minute. This is for all of your classmates who missed. Okay, hold on.
Oh.
Hold on. Hold on.
Cups off.
Okay, everybody. Can you see yourselves? And we're spinning. Go. Everybody spinning all the time. Are you on camera? Because I can't tell. Are you on camera? Are you on camera now? Okay. Jesper is the best. All right. Okay, I don't know if that's normal now. That's close enough. Because of this, iron is the only naturally magnetized element, as far as we know, in the universe. In fact, this is a hunk of iron that was just dug up out the ground. Yes, Chris?
Would something close to iron related
Becoming magnetic?
to like,
No, but there are, I'm going to show you. In fact, next week I will challenge you to bring in things that you think you would like to magnetize. So we can force some substances into being magnetized, permanently magnetized. For example, I always demonstrate in something that has enough iron to hold onto a magnetic field, like old scissors. Now, because I've been doing these demonstrations for 27 years, and I, usually just look around the classroom to see what's available. Yeah, I have many of these scissors are permanently magnetized. Yeah. So, not a great advantage to have magnetized scissors, right? Like, I always wanted to cut paper with a magnet. But can you think of something that would be useful if it were magnetized? Like a screwdriver, yes. And the screws themselves, yes. So, you can have permanent magnets and temporary magnets, but look at this one. This is a lodestone. It's dug out the ground. Nothing special done to it. It's magnetic. Isn't that groovy?
Do you mean magic?
A little bit. I don't know. I think we're in the 50s. So notice, too, that it seems to like to stick to what part of the rock? The tip. To pointy things. Anything that we've talked about? Yeah, exactly. Everybody hear Jody? Electrons like to jump off of pointy things. Electric fields like to emanate from pointy things. Magnetic fields behave the same way. All right, let's take a few notes. Okay. Oh, except for now the video's being covered up. Okay. Pull this a little closer. Okay. Lodestone is the the nickname. The scientific name for that rock is magnetite. And it's the only naturally occurring magnetic material. Now we can turn other things into magnets, and much stronger magnets than that. When you guys were in middle school, we did a fishing pole project, some of you, right? Yeah, how many, did yours win, Jim? Yes? How many paper clips did you pick up, do you remember?
All of them.
What is all of them? I don't know, because I haven't.
I don't know.
Anybody else? Any other winners in here?
No.
Second place? Yeah.
Didn't even fall.
So, yeah, there are other ways to make magnets, and we're going to do that. Lodestone is the only natural material, though. We also have, we're all sitting and or standing on a big magnet right now. Yes, the Earth has a magnetic field. And we're really glad it does. Anybody know why? Sun. What about the sun? Was that you, Justin?
No, it was Jim.
Oh, hi, Jim.
This is a little plug.
Oh, okay. Are you answering a question even though you're not in this class?
Yes.
You don't answer questions in first hour. You just second time through. That's okay. All right. Go ahead.
Radiation.
Yes.
I have extra.
No. Now, cosmic radiation is out in the universe. Lots of it. Much of what we get here on this planet is from our sun. If we had no like protective magnetic shield, what would happen? I mean, what would like right now? Let's say somehow magically the Earth's magnetic field, which by the way they think is due to flowing magma. What's the difference between magma and lava?
I was an outside reserve lava.
Right, outside versus inside. Yeah, they think it's due to flowing magma, which has a bunch of iron in it. Okay. So let's say that somehow magically the Earth's magnetic field went and just shut off. What would happen? No, it doesn't really hold the atmosphere together. The atmosphere would still be here. It's a good thing. We kind of need the atmosphere. It also helps protect us. It's going to be break time in 1 minute after you answer this question. What would happen to people? Yes. Vast majority of us would die due to radiation poisoning. Some of us, though, a very few, might become X-Men. And so here's the most important question of the day. If you were a mutant, what would your superpower be?
All the superpowers.
I do that.
See, now that's just greedy.
Not Superman.
All superpowers that have ever been thought of and might ever be thought of in the future. I want them all.
The ability to die.
I have a superpower, by the way.
What is it?
Oh, I can't tell you. Yeah, I'm a witch. Huh? Being a teacher is a superpower. That was very nice. It's Teacher Appreciation Week. Thanks, Ian.
Did you get a blizzard?
I did! It was really good. Strawberry, so good. And random kids that I didn't know delivered it, like freshmen, and I gave them hugs, and they were very uncomfortable. But it was really wonderful. All right, this is time for your 2-minute break.